So this is a little test example for your moments ladders problems. So statics of rigid bodies. So let's see. We've got some ladder that rests against the wall. What can we say? Let's say tan theta. That's theta there is equal to 5/12. And we can say what the weight of the ladder is 2m, or mass I should say. Let's say the mass of the ladder is 2m. It's uniform. Length 8 meters. Smooth wall. And rough ground. It's on the point of slipping. Find mu. Let's see if we've got enough information there. Okay, so the first thing you do is that in the shot, just about, is label all forces on your diagram and hope that your pen maintains. Is that strong enough? Yeah, I've got a Sharpie here somewhere. Like that. Oh, where's my Sharpie? Should move to this one. I'm just going to try a new pen. Right, so you've got let's call this A. I want to call this B. You're going to have reaction at A. So obviously the ladder wants to push into the ground and the ground's stopping it. Same at the wall. The ladder wants to push into the wall, but the wall stops it. So that's reaction at B. It's always perpendicular at right angles. Then also the ladder wants to slip this way. What's stopping it from slipping? Well, it's on rough ground. That means, so you're thinking friction. You see that? Obviously we've got mu as well, which is the coefficient of friction. So you've got friction pushing back against it, and friction is equal to mu times the reaction at A. That's what we've got. What else we got? We've got the mass of the ladder. It's uniform. It's 2 meters long, so it's going to act in the middle. Bang. And its mass is 2m, so we're going to have 2mg. And a new pen as well. Let's try blue. Oh, that one works nice. So we got 2mg. Are we going to be able to find this? What are we looking for? Mu. We might find it in terms of m. We might only be able to find it in terms of m here. Should we say what m is? Let's leave it like that. Let's see how this one goes. So 2, right? What have we got available to us? We can resolve forces going vertically. We can resolve forces going horizontally. And we can take moments. Now, usually we want to take moments about A, because that will get rid of both of these forces, leaving only these two forces. Because both of these forces act through A. So that means their moment about A is 0. Because remember, moments, so this is resolving. This is resolving. And this is moments. Remember, moments, that is force times perpendicular distance. So if a force acts through the pivot, and if we're taking moments at A, then A is the pivot, then the moment is 0. Right, so if we resolve forces vertically, we get the up forces equal to down forces. So we get RA is equal to 2mg. If we resolve forces horizontally, we get friction is equal to RB, or mu times RA is equal to RB. And if we take moments about A, so remember we need, right, that's the line of the direction of the force. We need that distance there, which is the horizontal distance of the line of direction of force from the pivot. So that's going to be that distance there is 1, isn't it? And that distance there is 1. So it's going to be that distance there, here, is 1. That's adjacent cos theta. So we're going to need to work out cos theta. Well, we know tan theta is opposite over A is 5 over 12. So opposite 5 over adjacent 12. So Pythagorean triple, that's 13, because 12 squared plus 5 squared is equal to 169, which is 13 squared. So that means from this we can get cos theta is equal to A over H, which is 12 over 13. So there we go. So moments about A. What else are we going to need? Well, this is the line of direction of RB. So we're going to need that distance there. That distance there is the same as this distance here, which is going to be 2 sine theta. So that distance there is 2 sine theta. And sine theta, we know from this triangle, sine theta is equal to O over H, which is 5 over 13. Okay, so if we take moments about A, we've got 2mg times 1 cos theta, and cos theta is 12 over 13, so times 12 over 13. That's the clockwise moments going that way, is going to be equal to the anti-clockwise moments going that way, which is going to be RB times by 2 sine theta, which is 2 times sine theta is 5 over 13. So we got that. Okay, we've got plenty of paper. Nice. Is that all on? Is that all on? Yeah. Okay, so then we have got how many unknowns and how many equations? We've got 3 equations and we've got 1, 2, 3 unknowns. So we can solve these. I mean, like a lot of the questions done there. That's what you want to do. Even if you're not sure, okay, if you're like, oh, solving those equations might be tricky, definitely what you want to do is label all the forces on the diagram, resolve vertically, resolve horizontally, and take moments. And that's every time. That's what you want to do. Right, so how are we going to solve these? So we want to get mu, right? That's what we're looking for. So mu is equal to, should we call this 1, 2, and 3? 1, 2, and 3 is equal to RB over RA from 2. Okay, well we know RA from there and we can get RB from there. So RA is equal to 2mg from 1. That's already done, isn't it? We're happy with that. And then RB, if we rearrange this one to make RB the subject, what should we do? Okay, let's do it the whole thing. So we got 2mg times 12 over 13 is equal to RB times 2 times 5 over 13 times through by 13. They cancel. Divide through by 2. They cancel. We're almost there, aren't we? Divide through by 5 and you get 2mg times 12 over 5 is equal to RB. So we've now got RB. So we got RA, we got RB. If we substitute them into this, we get mu is equal to RB over RA, which is equal to 2mg over 2m times 12 over 5. Everything's, well, not everything, but lots of things are going to cancel. It's a fraction over fraction, so that's equal to 5 over 12g, and that should be our value for mu. Although I want to check that because that doesn't look right. Mu needs to be less than 1, and that ain't less than 1. So I'm going to pause the video quickly, have a look at why that is, see if you can spot it as well, and I will get back to you shortly.